All right. I hope my sound is clear and audible all the way in the back. Okay. So thanks, Vinas, for the introduction. So I'm Amit Langote, and I work at Microsoft. Today I'm going to talk about hacking Postgres Executor for performance. I'll get to what I mean by hacking and performance, both these terms, in a minute. So about me, so I'm a Postgres major contributor and a committer. And the things that I've worked on mainly have to do with table partitioning. So I worked on adding the initial version of table partitioning, which other people filled in with other user visible features. And then I mainly worked on improving the performance of table partitions over releases. I've currently work at Microsoft, and before Microsoft, I worked at EDB and NTT, and my entire professional life, I've worked with the Postgres community on hacking and adding features, fixing bugs and improving performance. So here is today's agenda. So first, I would like to kind of clarify why we should talk about executor's performance and which aspects performance can mean different things to different people. So I would like to clarify which aspect of Postgres performance I'm going to focus on in this talk. And for that, to be able to do that job, I'll have to do some kind of a theoretical introduction to how CPUs work, and it's the things that you might have learned in college, and you might need a refresher on how CPUs optimize performance of when executing programs. And I'll then kind of give an overview of why Postgres is not able to utilize some of the CPU's performance characteristics. And it has to do with its execution model. So I'm going to focus only on the query executor part. There might be many other components of Postgres that are not able to use CPU properly, but my goal here is to only focus on the executor. So then after that, once we are familiarized with what the problems are, I will talk about a few things we have done over the years, some things as old as those that were committed in version 10, and some things that we committed into version 18, so not released yet. So these are small, localized fixes that allow Postgres Executor to use the CPU performance features better. And in the final part of my talk, I'll talk about some of the bigger things we could do to the executor in the core Postgres Executor that will make the performance of even better for some workloads. So yeah, and that will be kind of a high-level introduction. I don't have anything concrete an implementation plan or anything, but we have been discussing these things in the community. So there are some pointers to you could go and read more on what people are thinking about these larger projects. And finally, if we have time, I'll hope we'll have some. I can take some questions. And I'll just like to have a kind of clarify that I'm going to talk about CPU basics, but I'm not an expert in CPU architecture and micro optimization, microcode optimizations, or features that modern CPUs have. So I know the basics, and if you would please make sure that you don't get into the details of the CPU part. I can maybe answer your questions about Postgres and what we're doing in Postgres to kind of, but yeah, so I'll just, so yeah, first I would like to clarify what I mean by performance. So when you look at the executor, it's like a one component in the pipeline of, I hope it's visible, one component in the pipeline of query execution. You have the parser, you have the analyzer, the planner. Planner is pretty complex, but the executor is the part that I want to focus on. And there are two types of workloads. So first is OLTP. So these are for like short queries where the executor has a like a small fraction, but still, if you use, for example, prepared statements in which Postgres is able to cache the parse tree and the plan tree, executor becomes a larger portion of the overall execution time. So any performance issues of executor show up even for OLTP. But really, my main focus for this talk is OLAP. In OLAP, you're looking at like OLAP-style queries like aggregations, many joins, and these queries typically tend to look at the whole table, not just like a few tuples based on like some filter conditions. So you're basically looking at like millions of tuples processed like in one execution. So the things that I will describe later, like the way that executor is inefficient, these inefficiencies kind of add up if you like kind of add them over like the number of rows that are processed. So any overheads that executor has, it's a more serious problem for OLAP than OLTP. Yeah, I mean, we could improve executor for like better OLTP performance, but it is a more like kind of a dire requirement for OLAP. And yeah, I mean, if we can do things to reduce these like per tuple overheads that I was talking about, they add up to like significant performance improvements, as I will show in the later slides. Okay, so first I'd like to talk about some of the like hardware optimizations that are implemented on CPU chips. So the first aspect is cache locality. So you might be aware, like you think of caches in like software, like you know that memory is faster than disk, and disk like SSDs are faster than magnetic disks. So you try to like code around these kind of like memory hierarchy in software, but transparent like to user programs, CPUs also have like a hierarchy of memory. So CPU registers are the closest to the execution units of CPUs. Then we have L1, L2, L3 caches. So it's better if when executing a program, which are like a sequence of assembly or machine code instructions, they will be accessing memory from time to time. And if your program is laid out in a way that makes the CPU get most of the data from one of its caches, then the like performance is much faster. I'll get to like why it can be worse when it's not able to do that. Like if you might have heard of term like cache hit and miss. So if it's hit, then like CPUs are able to like execute programs faster. But if some instruction runs into a cache miss, it wants to read a memory that has not been read into the CPU caches, then you are going to stall CPU to make it spend like 100 times longer to like fetch that piece of data into one of these caches. And so there is like two pieces of data. Like there is like data and program itself, which is also data in some form. So there is like data cache and instruction cache. So these L1, L2 caches, they have like these divisions. So if you'd like to have your program to have like a sequential memory access, that applies to both the data and instructions. So for example, for data, if you lay out the data that your program is going to work on in a sequential manner, then when CPU fetches one byte, it will fetch the next, for example, 64 bytes to put into like on its L1 cache. And if the program accesses, just the data sequentially, then it's going to run faster. Similarly for instruction cache, like if you have like branches, like if the program runs from one instruction to the next and there is no kind of like jumps like which are unpredictable, then CPUs are going to find those instructions in the cache. But if that stops being the case, for example, if you have too many function calls, you keep jumping around from one function to another, and then your instruction cache hit ratio is going to suffer. So yeah, there's both aspects, data and instructions. The next aspect is pipeline execution. So CPUs are able to like work on multiple instructions at the same time, and it's able to do that because CPUs have like different execution units. So it's able to make different units work on different instructions in parallel. That's called pipeline execution. And when things are working fine, you see that like there you can run more instructions per cycle. But if your program does something, or if CPU runs into like cache misses or data or instruction, then it's going to stall because it has to then wait for like get a piece of data from memory onto its cache. And when that happens, for example, if instruction in this diagram, if the instruction force executor has to fetch some memory from fetch some piece of data from memory, then it's going to stop working, and then the next instruction also has to stop because the execution unit is waiting for the data to get into the cache. And similarly, like for instructions, like CPUs try to like predict. I'll get to it in a second. Try to predict which instructions it will execute next to keep the pipeline full. And if that system stops working, then it has to like if there are like any mispredictions, then it has to again wait and flush its pipeline. It has to fetch new instructions to replace the old one that were prefetched, and that adds to like you are essentially wasting cycles doing. CPU is doing nothing. None of its execution units are working on anything useful. So if you avoid these patterns, if you avoid cache misses by laying out your program in a sequential manner, the memory of the in a sequential manner, and if you reduce branching in your code and reduce the function call depth, then you can avoid these things. The next aspect of CPUs is speculative execution. So I mentioned that CPUs would like to keep their pipeline full. So if you consider that like programs are not always sequential, like you always see like if conditions and for loops have conditions. On each loop you check a condition to see if you should break out of it or not. And all these branches prevent CPUs from keep working on instructions in sequence. But it has something called branch target predictor. I have a typo here. It's branch target predictor. It tries to predict by looking at the pattern of execution which instructions will be executed next. And it will run those instructions in advance, kind of speculatively. So assuming that that's what will run when a condition succeeds. And this is often not the case. CPU might mispredict, and what happens then is the result of the instructions that have been kind of executed like preemptively, they have to be discarded. It's not put into registers immediately, so you don't get like a program corruption by something you have to discard. It's placed into something called reorder buffer, and from there, if the condition actually succeeds, so if CPU has predicted correctly, then that result is put into the actual registers. But if that doesn't happen, if the prediction was incorrect, then you have to flush the pipeline, and you also have to discard the work that was done. And some of the characteristics of how we write programs, kind of affects this seriously. So these cause like pipeline stalls, and it can, as you can see, you have wasted cycles essentially. And finally, so what causes branch mispredictions? So this is kind of like you have to look at why we have branch mispredictions. Why could CPU get into these situations? And there are like primary reasons. So you have like unpredictable branches. Like if you have to read a piece of data to take a branch, so you can't really be sure of what the branch will be taken unless you have read the data, right? And CPUs are not able to like predict if the condition will be true or not. But in some cases, it's able to do a good job, but in many cases, it's not. Another reason is indirect branches. So if you have a function pointer, if your code has many function pointers and virtual calls, which are, then the jumps, like the jump instructions in your program are not able to the branch target predictor is not able to predict which instruction will be executed next, because you have to read this function pointer's value to be able to jump to that address. And when you have like many function calls, like there's a stack, you have to put some the values of the current execution context onto the stack and go to the other function, and when you return, CPUs are able to keep track of where it should return after coming back from a function. Most of it is done in a software layer, but CPUs also have these tracking of where the program will jump next. But if you have frequent function calls, especially where you have a function pointer, which is like the jump address is only known at runtime. You have to do some computation to derive the address you would like to jump to. And so what can you do to reduce these mispredictions? So first option is to reduce branches. So if you can have less branches in code, I'll show you some examples of the patches we've committed in how we can reduce branches. So by flattening, I mean if you have long chains of conditions, nested conditions, then your code looks pretty nested. So you just have to try to make sure that you have less nested conditions, as less as possible. And for that, you have to maybe rethink the way you program. You have to replace indirect branches. So use function pointers less if that's possible, and make sure that there are more direct calls, so that CPUs are able to kind of do the preemptive execution correctly in more cases. There's another technique, loop unrolling. So instead of having a loop, you could just have a predictable loop with a predictable condition of exit condition. Then you could just write that loop as a series of instructions, and then you have fewer conditions to check and fewer mispredictions that could happen. So CPUs run machine code, and you have to write code in human programs. So you have compilers, and we've been told that compilers' job is to produce machine code that's optimized, and you hope that compilers are able to do that. And compilers actually do a good job in many cases. So the things I mentioned on the previous slide: inlining, loop unrolling, vectorization, flattening. Compilers, if you use the modern versions, they are able to do many of these things. But it's only true for programs that are smaller than Postgres. So why doesn't this always work for Postgres. Why can't we have Postgres builds where the binary or machine code is already, be able to like avoid all these CPU hazards, essentially. The reasons are Postgres is a very dynamic program. Like you are running, the Postgres is used to run queries that are not known in advance. Like you could write a database where you know what the query access patterns are, what the queries are going to look like, and if that's the case, you can write your program specialized for those queries and query plans. But Postgres is a general purpose database system, so yeah, there are many, the code base has to, like the planner executor has to consider every possible way that a query could come its way. And like many conditions are not known at compile time, so compilers are not able to do any of the things that it is able to do in other cases. Postgres has many functions. I mean, it's a big code base. It's many functions calling many other functions, and these function call stacks can get so deep because SQL and the plans are kind of recursive objects like trees. You can have like very like deep stacks, and that kind of makes things worse for the reasons that we discussed earlier. Memory access patterns are unpredictable. Yeah, well, I mean, when you're reading data, especially large amounts of data, it has to go from pages. The execution has to jump from pages to pages, and you try to, do it so that it accesses the memory sequentially, but it's not true in many cases. So yeah, we need to hack Postgres Executor and kind of rewrite it so that we can take advantage of these CPU optimizations better. So okay, does anyone have any questions at this point? I'd like to. I mean, it's the basics so far, so maybe not. Okay. Okay. In that case, I'll move on. So okay, so I'd like to describe how Postgres execution works, and it uses something called a volcano model. So it's pull-based, top-down. The program, the executor is given a program. I'm calling the plan a program, and that program is a tree-based. It's a tree of plan nodes, and it's very extensible because if you want to add a new plan node, you can just implement the interface for that node, and you can have as complex plan as you would like for implementing some SQL feature or for some optimization that makes the plans faster. So in this case, yeah, there's a nested loop join. It has two children, two sequential scans, and sequential scan calls storage to read data. Okay. And yeah, volcano model uses an iterator model. So in the iterator model, you start at the top. The executor will call the top node's iterator, and then it will call its children. So it will call the first sequential scan and then the second sequential scan, and it will the tuples that are read by sequential scan will then kind of bubble up. So yeah, I mean, like you can see that you have to call many functions. This is a very simple query plan, but for complex plans, it can mean that you're walking up and down the tree like many times. And what are the issues of this? Well, as you can see, there are many functions. You have a function responsible for each node, and you're going from one node to another by calling functions and all the way down. And then the control will return again back to the root node. And if you do this over and over for as many tuples as you want to return to the user, you're going to pay the overhead of these function calls. And yeah, I mean, each node has its own memory, to maintain its state. And it's in the current model, it's not like sequentially laid out. So for each node you call, you would allocate memory, and it will be on heap. in some place that's not predictable. And what this means is that executing this plan is going to lead to like scattered memory access for each node, and that means that the CPU cache usage is going to suffer significantly. And again, for each function call, you have many condition checks. For example, when you call the dispatch function, you check what function should be called for that node. For nested loop, you have to call exec nested loop. Next, you recursively call the next child node, and you would look at the node type, and call that to determine what function to call. So there are many condition checks in this execution. So because plans can come in many shapes, CPUs are not able to track the patterns properly, and it can do many mispredictions. And you know what that means for CPU performance. All right, okay, so these are the issues facing Postgres Executor, like the way it has been written. It was written like a long time ago, and maybe the developers didn't care too much about using hardware optimizations like CPU pipelines and so CPU cache hierarchy, and we are still using the same code base. So when we look at benchmarks like TPC Edge and other OLAP benchmarks, you start to see that it works very poorly on modern CPUs compared to some other specialized OLAP databases. So this work has, these benchmarks and the work to improve it was started quite a while ago, and there were proposals to kind of rewrite the executor from zero, from scratch, but those are large projects, and they never kind of got done. We had ideas what to do, but the large projects never got done. But I'll get to the larger projects in the end. But what we found out is that we could do some localized fixes for different parts that will allow to kind of reduce the overheads significantly. So I have 5 projects or patches, so I'll just go through them as quickly as possible. So plans have expressions, so you have where condition, so that where condition gets represented as an expression. And before version 10, these expressions can also be very nested. Like you can have, if you look at this expression, you have a tree. I guess you are familiar with how expressions are represented as trees. And before version 10, we had a tree walking based execution model, which was inefficient for the reasons I was discussing earlier. So you have function call for each node, and the more complex your expression is, the more overhead it's going to cause due to excessive function calls and poor cache efficiency. In version 10, this was all kind of rewritten from scratch, and now what you have starting from version 10 is just one function which takes care of, which has the code for all the expression node types that you have. So instead of a tree walk, now you just jump in the same function, within the same function, from the code for one expression node type to the other. And this code has, the new code has less function calls. Of course, there will be a function calls because operators in Postgres are implemented as functions. And you have to call a function to, for example, do the plus operation or equality. And there are these functions, but overall, the expression itself, the whole expression itself doesn't lead to recursive function calls, which makes the CPU's branch target prediction work better. And it has shown significant benefit for many queries in TPC-H benchmark. I didn't put them on the slides, but if you go and look at some of the old presentations on this topic, there's a whole presentation on this back in, like, I don't know, 2017 or something. The next is reducing exec proc node overhead. I mentioned that a plan is a tree of nodes, and before this optimization, you would call exec proc node for any given node, and then for its children, you would just call exec proc node. And exec proc node is a dispatch function. It will look at the node's type, and it will jump, or it will look up the function for that node and will jump to it. So you're calling exec proc node for each node, and then again calling that node's function. And CPU is not able to, once it reaches exec proc node, it's not able to tell which function is going to jump next. So this causes like many indirect jumps and branch mispredictions. So this was replaced by remembering the each node's function in its plan state. So you don't call exec proc node to determine where to go. You will just look at the node's plan state itself, and you have the function pointer predetermined at the plan initialization time. So you take some work that the executor was doing at runtime and moved some of that to plan init time. And yeah, this reduces like many indirect function calls, and reduces CPU stalls and branch mispredictions. This also made performance better by itself significantly. So this is something not part of the executor itself, but the module that it calls. And it's a function in heap AM. So if you have a sequential scan basically wants to read all tuples in relation. So it will call heap AM's heap get page. So it's a function to get tuples on a given page. And the previous versions of heap get page had many conditions that were done for each tuple, even if those conditions remained the same for each tuple. So for example, the condition to check if the tuple is visible, and the condition to check if it's visible to snapshot in the serializable case, all these conditions were checked for each tuple, and this caused like a lot of mispredictions and CPU stalls. In the new version, what we did is we created a separate function for this loop, and it took two parameters. It will take all visible and check serializable flags, and then use, and this function is inlineable function, and compiler is able to create like specialized versions for like all visible true and all like different combinations of the true false values of all visible and check serializable. So these, you calculate this flag once for a page, and then you don't have to, in the new version, you can just assume that the tuples are all visible if, for example, all visible is true, and you reduce branches a lot. So this allowed us to make sequential scans run significantly faster, especially for all visible pages. You might know that vacuum is able to set pages to be all visible. And if that's the case, then with this particular change, sequential scans were able to run much faster. The next one is something that my colleague, so the previous things were done by my colleague Anders Freund, and this one, optimizing tuple deforming, was also done by my colleague David Rowley, and he worked on it for like a few months. And so tuple deforming is, you have to break a tuple into its columns. Executor is not able to work on heap tuples directly. It has to have like this tuple broken down into its columns, and tuple deforming is the process to do that. And in the earlier, the thing that it uses for this is something called tuple desk. It's called tuple descriptor, and it has information about each column. And before this change, tuple desk stored the whole PG attribute catalog entry as it is in it, and each PG attribute entry is longer than a CPU cache line. So not all information is needed for deforming. So yeah, I mean, deforming code was like going to memory more than it actually should have. So what David did is he replaced the PG attribute struct by a compact attribute struct, which is 16 bytes. So now you're able to fit 4 columns information in one cache line. And yeah, that led to like significant improvement in cache locality. The next is alignment. So tuples can have fixed width attributes and variable width attributes. So you have to check for each tuple, like what's the length of that column is. And this code used conditions that are like significantly like branch heavy, and he replaced that with something called type align, which has no branches. So this also led to like this branched code with many branches to something that has no branches. And because you're doing this for each column, the more columns you have, more overhead you had before, but now with this change, that overhead is gone. And finally, slot deform heap tuple. It's the body of the main loop that will go over all the columns and create like values for each column. Now is an inlineable function, and we were checking a few conditions for each tuple, for each column separately, but it didn't need to be done. For example, if you knew that a tuple has no null columns, everything is, for example, not null, then you shouldn't have to check whether a column is null for each column. Okay, and there's something called slow path. Slow path is the code to determine which offset a given attribute is at in a heap tuple. And if you only have like fixed width attributes, you don't need to check the length or you didn't need this low path for each column. And now in the new version, we avoid these null checks if we know that there are no nullable columns. And also there's some code to like figure out that slow path doesn't need to be taken for maybe, for example, if you have 30 columns, you can use fast path for like up first 15 columns, then it won't check if it should do like slow path check. And from that point on, it will use the slow path function. And this also led to like significant improvements because you have fewer conditions in the main body of the main loops. And David did extensive benchmarks. He checked this on many CPUs, and he saw that these optimizations of compact attribute, alignment, and slow path null check attribute optimizations led to, well, 5 to 25% reduction in query time, depending on how many columns you have, how many variable and fixed width attributes they have. In best case, you had like 25% improvement. Finally, this is something that I worked on. So exec-scan is a common function used by the leaf nodes, so sequential scan, index scan. They all share this code to check some conditions, like whether the tuple should be fetched from a special place called eval plan qual, which is something we have in Postgres Executor for implementing read committed isolation level. And then there's code to check if there is conditions to check for a tuple and whether projection is needed. Sometimes you can just return the whole tuple, all columns to the parent node, but in some cases you have to select which columns to kind of pass on to like the parent node, and you need projection for that. So yeah, I mean, this one big function had conditions that check eval plan qual, and projection, and that led to overhead if you are scanning like many tuples. So the solution that we came up with is to move the main body into this inlineable function, exec-scan extended, and it has parameters for eval plan qual state, qual, and projection states. And now we have these 4 specialized versions. So the first one we know that there are no calls to check and no projection to be done. So it just fetches the tuple and returns tuple. No branches for checking call and no projection. And again, we have with qual, with proj. With qual has to check the call, and with proj has to apply the projection. And finally, with qual and proj, it's the same as what we had before, but like in many cases, you're able to use one of these specialized functions that have less branches and less overhead. And again, I was able to see, even with this just localized exec scan fix, I was able to see up to 5% execution with sequential scan heavy queries. All right, I guess I have 5 more minutes. I'll just go through the remaining future projects as quickly as I can, and then I'll maybe take some questions, Okay, so the first thing we considered doing is replace our tree walk-based execution model into a program. And that program would be a linear program of opcodes. So for each operation that a plan has, you have an opcode, and you would have just one big function with the kind of like dispatch code for each node. And your plan would have a new layout. So you now get a tree of plan nodes when you do explain. But with this opcode-based execution model, if you do explain, you can see the program that it's going to execute and in the sequence in which it's going to execute. And in Volcano model, you start at the root node, and before you do any actual useful work, you just call functions, right? You keep calling functions until you get to the root node that actually reads tuples from disk. But in this opcode-based execution, we kind of turn it inside out. You start with sequential scan, and you because it's placed in the beginning. I mean, there is sort, but let's forget that for a second. So you go straight to sequential scan. You read a tuple, and you check conditions if needed, and you pass that tuple to the node that needs it, the parent node, and the parent node will hand it over to its parent node. And what this means is that you start doing useful work from the beginning, so you don't. And again, this opcode-based execution doesn't have recursive calls to go to for each plan node's operator. So this implements a flat execution model, and if we are able to get this to work, it's going to lead to, I think, a significant improvement. But it's not really just, this is not the end goal. Having a single function is important for the next things that we would like to do with it. So the next thing we would like to do is do batch processing. So Volcano model is tuple at a time. So you start at the top, you go at the bottom, and what you've done is spend all that time just working on one tuple, right? And batch processing is you make Postgres, work with a batch of tuples, like a set of tuples, not just one tuple. And what that means is that you are going from function to function, but doing it for a bunch of a set of tuples, not just one tuple. So the cost is kind of amortized across tuples. And you're not. In the previous slide, I mentioned we have one function, but you could do that separately, and you could just do batch processing with the existing model. So just instead of just one tuple, we just pass batches of tuples. And this will, again, amortize the cost of function calls and etc. across tuples. And with batches, you have the option of using a layout that's vectorization friendly. So you maybe still use the row-based storage, but when you read it, tuples, the batches of tuples, you kind of transpose those tuples into columnar format. And once you do that, like you can use SIMD operations for like vectorized operations, and instead of like doing an operation for each column, one row at a time, you can do that for like multiple columns at a time. And again, amortize the cost across multiple columns, multiple rows. Yeah, and finally, there is an option of compiled execution. So we, in the previous versions, like previous approaches, you are still interpreting. So you still are doing the, like, you still have Postgres kind of interpreting your plan, but there is a way to like take like a version of the plan, for example, the single function version, and pass it to like LLVM or other JIT providers and have it compiled. So what you're going to do with that is you're running a program that's potentially significantly optimized for like to run on CPUs. So with that, I guess you would have less function pointers and many other things that are problems for interpreted execution. And we already do this for expression part of the plan trees, but the goal here is to do this for the entire plan. And yeah, I mean, it has maybe many steps. We need to get opcode-based executor working first, and then we get a single function to compile. So yeah, so all these things I mentioned have been kind of investigated, but we decided that doing the smaller things that we did was maybe a better use of our time. And each of the bigger projects are going to take, I don't know, a year or a couple of releases to stabilize. So yeah, but the goal is to start looking into these projects. I think that's all I have. If you have any questions, I don't know how much time we have left. I think